Hi, Assalamualaikum, and a very good day to everyone. Welcome back to our class. And today we're going to continue on the 18 electron rule, or EN rule, or effective atomic number rule. I hope it is clear to you now what the rule is now, that EAN is actually representing the total number of electrons in any given metal atom. It is not the number of electrons accumulated from the ligand as well as from the metal. It is only representing the number of electrons in the given metal atom. Now, I have given you these practice exercises and I have glimpsed through all the answers that you have posted in the Padlet. Alhamdulillah, most of you did it very, very well. So let us refresh what did we do. The first one is to deduce the probable formula of the simplest carbonyl compounds of nickel. Now, with or without hint, this question actually was asking you to find the best number of ligands that could be attached to your nickel. So how do we know? It depends on the 18 electrons rule. So based on that, we should know how many ligand that we should have in any given metal complex. Okay. Now number two, 18 electron rule to predict the number of covalent ligands. Again, okay, the same thing. Now you should have known that nickel and iron are coming from which column in your periodic table. So from that number alone, you can predict how many carbonyl that you can have in these complexes. Because one carbonyl can give you 2 electrons. So how many carbonyl do you need in order to make it 18 electron in the iron or nickel? And then the third one suggests why vanadium CO6 hexa carbonyl is easily reduced to its negative form. So in order to understand this, you have to calculate the valence electrons for each species. So which one is more stable? So that is the hint for this answer. So I think we are okay with these practice exercises. If you are not, then you are always encouraged to ask me questions in Padlet or in the WhatsApp group. I could not congratulate you enough for your participation on a Tuesday, because seemingly and apparently your participation wasn't as what as I expected. Maybe you can do something. So I believe that when the questions were posted and asked in the Padlet, then the WhatsApp group will be much quieter. So probably today we are going to have few questions, and those questions will be answered in our WhatsApp group. So I hope full participation from all of my students. Can we continue? So these are examples of metal complexes. We have mononuclear, we have polynuclear, we have one metal for mononuclear, we have two metals for dinuclear. We can have more than two metals, like for this one, we have trinuclear with three metals. We have gone through all this. So you can try to find the effective atomic number for some other metals complexes. Like for example, what would be the best EAN for cobalt in this complex? Or what would be the best EAN for this compound, for this complex? So we have M here. M can be cobalt or rhodium. So you please find the EAN for this one, okay, for this compound, both cobalt and rhodium, as well as for this one. Okay, so let's see how many of you can get this right. And please post your answers not on Padlet but in our WhatsApp group. Now today we are going to learn that even though to be a stable metal complex, so metal should have 18 electrons, the valence shell, but that is not always the case. There's always exception to this general rule. So we want to know why we could have such exception. When you look at this transition metal series, from this table we understood that the middle ones are going to get 18 electrons, obeying EAN easily. But for the early transition metals, you're not going to get 18 electrons, but you're going to get less than that. It can be 17, can be 18, it can be 16. Why? Because there is a steric factor. So this steric factor is induced when the size of your metal atoms is too small. So early transition metals are not going to obey 18 electron rule because the size is too small, inducing steric factor. So you cannot add more ligand to the metal due to this small size. And the late transition metal series like cobalt and nickel, and rhodium and palladium, they are going to have 16 or 18 electrons. Later you can see that for square planar complexes like nickel and palladium, they're going to get 16 instead of 18 electron. Why so? This depends on the energy factor. This energy factor will be explained more slightly later. Okay, so as for now, things that you have to register in your mind is that the middle series of your transition metal, we're gonna get 18 electron easily, obeying 18 electron rule. But for early transition metals in the series will get less than 18. The same thing for the late transition series. So the early transition series, the factor is steric factor, and for the late transition metal, the factor is energy factor. Now let us look at the exception to 18 electron rule. Reasons for breaking the 18 electron rule. Rules are made to be broken, people say. So why this rule can be broken? The first reason is your transition metals early in the series, such as titanium and vanadium, as I said, small sizes introduce steric hindrance. So this will limit the ability for the metal to take electrons more from the ligand, hence having less number of electrons in the metal. So stable compounds for these metals containing 16 electrons shell, 16 valence shell electrons. Okay, so they are not going to get 18 electrons. Now the second reason for metals late in the series, such as copper and zinc, it is common to find 16 valence shell electrons. Why? Because the 3D orbitals have a very low energy to the extent sometimes this energy can be in your atomic core. So in order to understand this better, look at this graph depicting the increase of binding energy against the number of electrons or the effective nuclear charge or the energy of your orbitals, 3D, 4s and 4p. So copper and zinc are metals from the late series. Okay, so you can see that as you go further from cadmium to zinc, the energy of your 3D is going to be lower and lower and lower to the extent it is now in the atomic core. Now, what is atomic core? Atomic core is the shell containing electrons except your valence electron. So the easiest one, for example, we have sodium, Na. This sodium has 11 electrons. So the valence electron is 1. So the atomic core would be 10 electrons of sodium. I hope you are clear with this. So you can use this analogy and apply with these metals. So you understand this better. So atomic core. So when your 3D orbital's energy is now in the atomic core, it's getting more stable and stable because the energy is going to be very, very low. They are not having high energy So it is very difficult for the electrons to be participating in forming any bond. So that's why the conclusion that we can make here is that for the transition metals, for the late series of transition metals, they are having issues with energy. Issues as in the energy of your 3D orbitals will be very, very low, to which extent they will be in your atomic core. So they are too stable to be participating in forming any bond with your ligand. If you're not clear with this, you can ask me later. Okay. So effective nuclear charge increases across the series. We all know this as because your atoms are arranged according to the proton number. The higher the proton number, the later they will appear. So as the number of proton increases, the effective nuclear charge also increases. So that's why the 3D and 4s orbitals drop in energy faster than that of 4p. Okay, so 3D orbitals are part of the atomic core and too stable to participate in bonding. This is what I said just now. Now, 16 electron species. So most stable organometallic compounds obey 18 electrons rule. However, some complexes are stable with less than 18 electrons. Okay, this depends on the energy and then the nature of the bonding with the metal and the ligand. So the most common one would be from group 9 and 10. So, for example, the square planar complexes commonly have D8 electron configurations. Rhodium, iridium, nickel, and palladium. Okay, the most common ones are zest salt and also Vasca's compound. You can tell from this structure that it does have less than 18 electrons. Okay. The second thing that we want to look at is the odd electron species. So odd electron species meaning they have odd number of electrons. So instead of 18 or 16, they're going to have 17, for example. So in this case, we have VCO6. We have done this in the previous practice exercises. So in order to make it 18, you can accept an electron from a reducing agent. That's number one. Or in order to be 18 electrons, they have to form a dimer. You have to dimer the complex with another complex by forming metal to metal bond. So we're going to get 18 electron species. So what is metal to metal bonding and how is it related with the 18 electron rule? You can see here that from the 18 electron rule, we could use it to predict the number of ligands that we could have in any metal complexes, like what we did in the previous exercises. So we are going to know whether or not it is stable from the number of electrons around the metal. So look at this example. We have this. I'm sure you are familiar with molybdenum and carbonyl. So what is this? So this is actually cyclopentadienyl. So cyclopentadienyl is the type of ligand that carries negative charge, and it can give you 6 electrons to your metal. So as usual, we count the number of electrons for molybdenum. Since your cyclopentadienyl is negatively charged, in order to balance that charge, your molybdenum must be positively charged. So it's coming from column 6, 6 electrons minus 1 is going to be 5. Cyclopentadienyl, negative 1, 6 electrons. Your carbonyl, 3 carbonyl times 2, you're going to get 6. So if you total up this, 6 plus 6, 12 plus 5, 17. So it is not 18 yet. So it is not stable yet. So in order to make it stable, you must form a dimer with the same molecule by forming MO to MO bond. So one bond is 2 electrons. So if you want to find the number of electrons for one molybdenum, it's going to be 1 electron. So when you total up, you're going to get 18 electrons. Okay. So without this MO-MO bond, you're going to get 7 electrons. So you can get 18 electrons easily by dimerizing with another unit. Okay. So that's number 1. You can achieve 18 electron rule. You can achieve stability for odd electron species by dimerizing with another unit through the formation of metal to metal bond. Or the second one, it can be done also by replacing carbonyl with some other 2 electron donor ligands. For example, we have phosphines here, PR3, and also phosphites. These ligands also donate 2 electrons. Or for nitrogen-based ligands like isocyanides, this ligand also will give you 2 electrons. Okay, if you replace your carbonyl with other 2 electron donor ligands, you're going to get 18 electron species. Or second one, by adding or subtracting electrons. If you replace CO with bromide, it's going to give you MoCO5. So one CO is replaced by bromide and Br negative. So this MO going to give you MO plus. Okay, and then replacing MO with isoelectronic Mn plus. So Mn and NO. So both coming from different column, right? So for molybdenum, it's going to be molybdenum column 4 and manganese column 5. So isoelectronic meaning they are having different number of configuration. So for Mn to be isoelectronic with MO, it should be plus here. So you have to minus 1 electron. So you're going to get a stable configuration. Now this table below give you the idea on how many valence electrons that can be contributed by your ligand. Okay, so you don't have to memorize this. When you are doing more exercises, you're going to, this thing will be stuck in your mind. Okay, so what did we learn today? So we learned that there is an exception to the general rule of 18 electron rule or EAN rule. Certain metals can have less than that. For example, the early series of your transition metals or the later series of your transition metals. For the early series, the factor is steric factor. The size is too small, hence it cannot accommodate more electrons or more ligands, hence having less than 18 electrons. For the late series of your transition metals, they are having issues with the energy. What kind of energy? So the 3D and 4S energy will be dropped, in fact lower than that of 4P, to the extent at which it will touch the atomic core. When it touches atomic core, it's getting more stable, having low energy. So it's very difficult for them to participate in forming any bond with your ligand. That's the lesson number 1. And the second one, we learn on how odd electron species can be more stable by having 18 electrons in the valence shell orbitals, in the valence shell or in the valence orbital. So this can be done by accepting, by forming metal to metal bond, or second, we can replace the CO by any ligands and add or subtract the electrons. So that's all for now. If you don't understand, please ask me in the WhatsApp group or in the Padlet. Thank you very much. See you in the next video.